Hello, thank you for joining us today for our webinar. My name is Greg Skidmore and I am the Director of Propagation Software and Government Services at Remcom. Today, my colleague Tarun Chawla and I will be walking you through a demonstration that uses Remcom simulation tools to design a complex MIMO antenna for a 5G base station and then evaluates its potential performance in a fixed wireless access scenario. Fixed wireless access is a key application for early 5G rollouts, with a goal of providing last-mile broadband connectivity to homes and businesses. In this webinar, we will design a millimeter wave MIMO antenna for 5G fixed wireless access, and then we'll evaluate its potential performance in a suburban neighborhood fixed wireless access scenario shown in the diagram to the right. The overall objective is to demonstrate a simulation-based methodology for designing complex systems and then assessing their performance in realistic virtual environments. And while our application in today's webinar is fixed wireless access, this methodology can be applied to any of the many complex 5G scenarios that will be coming online in the next few years. Before we begin our demonstration, we'd like to give a quick overview of our company for those who are new to Remcom. Remcom was founded in 1994 by Dr. Ray Lubers, a pioneer in finite difference time domain research, along with Dr. Chris Penny and Mr. Scott Langdon, who are still our principals today. Remcom is a market leader in electromagnetic simulation software, providing innovative tools for design and analysis of just about anything that involves radiation propagation or scattering of electromagnetic waves. We're located in State College, Pennsylvania, and we are a small business, allowing us to focus on collaborating and providing quick answers and responses to our customers. We also perform a great deal of research, both internal and under research contracts, and we pride ourselves on our ability to put cutting-edge technology into our products where it can be used by our customers. We have an international presence with a global distribution network, and our business involves both commercial sales and government contracting. The two core products that we're going to be using today in our webinar are XFdtd, which is a 3D full-wave solver used for antenna design, EM scattering, and a number of other detailed applications, and Wireless Insight, which is 3D wireless prediction software with a core focus on urban, rural, indoor, and other complex propagation environments. With that, I would like to turn it over to Tarun, who's going to walk you through the process of designing an antenna array in XFdtd.
Appreciate it, Greg. My name is Tarun Chawla, and thank you for taking the time to join us today. In the next several minutes, I'll be walking you through a design of a planar array of 64 patches used as a massive MIMO base station, simulated with Remcom's XFdtd EM tool, or XF for short. This patch array will operate at 28 GHz and is located on top of a substrate. We look at forming beams with this array in two directions to maximize coverage over the far zone sphere. We begin by creating a single patch and optimizing the position of the source feed. This can be done by varying the location of the feed and observing the change in return loss of the patch at 28 GHz. Based on the return loss response of the parameterized feed position, shown in this plot, we determine that the optimal position of the feed is about 0.75 millimeters away from the center of the patch. We can then create an 8x8 array quickly using the pattern feature in XFdtd. I will switch to the XF UI to demonstrate this. The size of this ground plane is about 52 millimeters in both X and Y. Spacing between each element is predetermined. The number of instances that I will specify to create the 64 elements is 8 in the X direction and 8 in the Y direction. This gives us the ability to specify a 64 element array very quickly in the tool. We then proceed to perform some phasing calculations. Here's an example of a weighting function that is chosen for this 2D array. This equation steers the array towards the wave vector in the desired direction. Let's assume an example direction as shown in this chart, where phi is 45, theta is 45, and phi is 60. Based on the weighting equation, we backfill these values into each element of the 64 element array. XFdtd can quickly import these values from the table and automatically assign each phase to the appropriate feed. All of the components here have a parameterized value, which means when a new phi or theta computed table is generated, all of these values are automatically updated. We then get to steer the array in multiple possible directions, like in this case. This is the array when phi is set to 0 and theta is set to 0. The peak gain is determined to be 23.2 dBi in this case. Other varying locations of the beams in XY in the YZ plane, and beams in theta 45 while varying about in phi. Using a script for a desired feed combination and input power, we are able to generate the max EIRP CDF plot, which is the effective isotropic radiated power over the far zone sphere. If all the elements in this array were to be active at 23 dB milliwatts, 78% of the far zone sphere has positive gain. Also, for this array, the max EIRP will be 45 dB milliwatts. I will quickly switch to the UI again and talk about effects of the performance of each of the elements and the use case for taking this base station and putting it into an outdoor environment. We export the far field gain patterns of each element of this array, and we'll use it in the Wireless Insight channel modeling tool. The way to quickly do that is to load each of the gain patterns, visualize them like so, and export the far zone sensor gain values for all of the elements. In this case, we have 64 gain patterns. The user simply right-clicks on the active port and says export to Wireless Insight Array. Once that is done, the user will get a folder with an XML file which is pointing to each of these 64 patterns of this array. Now Greg will take this array and put it in an environment using the channel modeling tool Wireless Insight.
Thank you, Tarun. Next, we'll take the antenna array that Tarun has designed in XFdtd and load it into Wireless Insight, where we can place it into a full fixed wireless access scenario. So the antenna is a 64-element planar array, and we're going to be using it as a base station for suburban fixed wireless access. In the diagram to the right, we can see the array placed at one end of a street. It's been placed at a height that's consistent with being on top of a utility pole, about 12 meters up. And we did our simulations assessing a single component carrier with 100 megahertz bandwidth, which is consistent with 5G NR, and at 28 gigahertz, the design carrier frequency. The scenario also includes consumer premises equipment, or CPEs, placed on multiple alternative configurations at each house that we'll talk about a little bit later. The focus of this study is on a single street in front of the base station. Now, if we pull up our Wireless Insight software for a moment, we can see our scenario a little further zoomed in, and we can see the antenna array, 8x8 array that was designed by Tarun in the previous slides. We can open up our antenna editor, and it shows our XF MIMO array at 28 gigahertz. The antenna patterns have been imported in. As we step through the different array positions, we can see that we have individual antenna gain patterns that have been developed during the design process with XF and now imported into Wireless Insight to give us a more realistic characterization of our antenna patterns. So looking a little closer at this array, we've imported the array. It's vertically polarized in each of the elements. We then assign an output power. In this case, we've assigned 37 dBm for the power. We've given it the frequency of 28 gigahertz and the single component carrier. As we'll discuss later, we're going to do analysis of a single component carrier, but the work that we do could be extrapolated to multiple component carriers and carrier aggregation. So the CPEs, or consumer premises equipment, have three configurations. The first is a rooftop configuration, shown at the bottom left. This is typical of something that would require a technician installation. And so in an ideal world, some of the other two may be more preferable. The first is an indoor, which could be consumer equipment that is placed near a window, perhaps on a windowsill, or outdoor window-mounted unit. This third option is intended to represent some things that we have seen vendors devising as a creative approach to avoiding window attenuation at millimeter waves. So these are units that can be placed on the exterior of a window, and then they can communicate with devices on the interior of the window, which then propagate from there with the Wi-Fi to interior devices. So for each of these CPEs, we have assumed that their antennas are actually arrays that have beam steering. But to model this beam steering, we've used two omnidirectional antennas, cross-polarized, and these are intended to represent two cross-polarized beams to allow for 2x2 MIMO in our later analysis. However, since these are beams, they do have a gain. They're fairly directional. We assume that the indoor systems have a 12 dBi gain, and that the outdoor systems may be able to have a slightly higher gain of 18 dBi because they can be a little more directional. They only need to be able to beam steer toward the outdoor directions. All of the materials in this scene have been defined with material properties based on the types of materials that they are. So for the houses, the walls have been designed to be sheetrock on the interior and brick on the exterior. Between the brick and the sheetrock, we have plywood and 2x4 studs that are being modeled as air gaps between the different layers. So it's a multi-layer material. For the windows, we have another multi-layer material, in this case 2-pane glass with air between the panes. And then the doors are 2 inches of wood. Garage doors are made of metal. The roof is asphalt shingles. Then for the environment, the roads are assumed to be made of asphalt. The street corners that we can see a couple of are concrete. The grass is set to properties of a generic ground with a medium level of moisture, sort of an average level of moisture in the ground. And then we have a whole series of foliage volumes that are used to represent trees and bushes throughout the scene. These will be modeled based on a model called the Weisberger model that we'll describe a little bit later. Now, millimeter wave has several challenges. One of the first and most commonly known is the high path loss. At 28 or 30 gigahertz, you can expect 15 to 30 dB more path loss than you might expect at some of the lower bands, like the sub 6 gigahertz, 1 gigahertz bands. A second problem that we have is atmospheric absorption. As we go up in frequency, we can see from the chart at the bottom right that the absorption levels go up. And there are certain resonances at particular frequency bands. There's one around 21 gigahertz for water vapor absorption, and there's one around 60 gigahertz for oxygen absorption. 60 gigahertz is a particularly attenuating one. Fortunately, 28 gigahertz is in a region that does not suffer too heavily at about 0.13 dB per kilometer, and the short ranges that we're dealing with, this should be a negligible effect. However, if we went to longer ranges, these effects can become important, and XFdtd's models in the Wireless Insights suite have been designed to include them. Next, we have the high penetration loss from walls and trees. This can be severe at higher frequencies, especially 28 gigahertz or above. We've prepared a chart here to the right that shows some examples. 3GPP has a model for IR-resistant glass. This glass can have attenuation at 30 gigahertz of more than 30 dB, and many modern office buildings are using IR glass. We also have 20 centimeter concrete, and we can see as we go up in frequency, the attenuation from a concrete wall of this type can also become extremely high. Next, if we look at a regular old-fashioned type of glass like the two-pane glass windows, we can see those attenuations are not too bad, but they're certainly much higher when we're up in the 20 and 30 gigahertz range than they are down at 1 or 2 gigahertz in the traditional frequency bands. And last, we have trees. There are two lines shown here, a light green and a darker green line that represent the attenuation from trees. Foliage attenuation can be quite severe as we go up in frequency and gets worse the more trees that we're trying to penetrate. But just looking at a single tree in the bottom line, we can see that attenuation might go from a few dB to perhaps 6 or 7 dB. If we go through 3 trees or more, we may find attenuations approaching 16 or 17 dB as compared to perhaps 7 dB at the lower frequencies. So all of these effects can significantly reduce the signal and the ability to propagate over long distances. And another item that's a problem is the diffractions around corners are very weak at the higher frequencies. They're often thought of as line of sight models, or line of sight frequency bands. And so all of these things make it difficult for signals to propagate far. Wireless Insight's array models capture all of these effects, which make it possible to estimate what kind of effect they're going to have on the final results. Now, fortunately, 5G offers some things that can help to overcome some of these effects. One of the big ones is MIMO beamforming, and spatial multiplexing is another. So in this study, we evaluate 3 different MIMO techniques with the base station antenna. The first couple are beamforming. So in the last session, Tarun walked through some of the different pre-coding weights that can be defined to set up beamforming with different beams. So in our first type of beamforming, we use these predefined beams defined during the XF design process. We transitioned those and then converted them into a table that can be read into Wireless Insight so that Wireless Insight can use those beams as a table of potential beams to choose from. Using this method, Wireless Insight will choose the best beam to each different CPE position. And what this is trying to model is a condition where there are several fixed beams, and perhaps through beamforming, the CPE can determine which of the beams is the best, pass that information back to the base station, and then it can use that beam for the communication. The second type of beamforming is adaptive beamforming using maximum ratio transmission. This creates a beam based on the channel conditions to maximize the gain to any particular position. This requires the base station to have good channel state information, so in practice there can be some challenges with this. In a TDD system like the one that we're presenting today, it is possible to get channel state information from the CPE transmitted up on the uplink and then use that channel state information on the downlink. However, there are challenges and differences that have to be overcome to make this possible. So in practice, the MRT ends up being a slightly more complicated design, but we will use this one in our simulations as well. And then the third is spatial multiplexing. We use a technique called singular value decomposition to create isolated data streams. Over on the right, we can see the differences between the beamforming and the spatial multiplexing. In spatial multiplexing, the data received by 2 different antennas is used through singular value decomposition to isolate 2 different data streams. This doesn't give us as high of a signal-to-noise ratio as the beamforming, but it does allow us to potentially have multiple data streams and increase our data rate. So the predefined beams that Tarun talked about earlier, when we converted these into a table, we were able to use them as inputs into Wireless Insight. We then did a quick analysis in a study without any geometry in it, just placing a sphere of sensors around our transmitter so that we could evaluate the beams. So we created a table with beams that extend from plus or minus 60 degrees in the horizontal direction and from minus 30 to positive 10 degrees in the vertical direction, each with 10-degree spacing. This gives us a total of 78 beams, 13 beams wide by 5 beams high. We then did a quick assessment of the beams to make sure that they were working and to demonstrate them here. So on the right we have a plot, and it shows in red the bore sight beam at 0 degrees elevation and azimuth, and we can see that in red. We can also see that down below. This is our 0-degree beam. And then we have our 60-degree beam, 60 degrees off bore sight, shown in the diagram to the bottom left. And that's plotted above in the horizontal plane in blue. When we combine all of the beams in the table over a horizontal sweep, we get the plot that's shown in green. And we can see the peaks of each of the individual beams as we were creating this plot. What this green plot represents is what different CPEs or different receivers in any direction could receive when they determine the maximum beam and then use that beam for the downlink communication. And when we compare that with maximum ratio transmission, which is shown in orange, this is somewhat of an optimum beamforming technique. We can see that the beams that we formed and the maximum ratio transmission are very close. And this demonstrates that the pre-coding tables should give us a very good set of beams that we can use in our simulations and perhaps in the design itself. Next, we have the receiver techniques. For the singular value decomposition that we described, the spatial multiplexing, the transmitter and the receiver work together to create the multiple streams of data. However, for the beamforming, the receiver can apply some additional techniques to further increase the received signal. So each CPE was assumed to have enough antennas to form two cross-polarized beams, which we modeled as two antennas for this scenario. For spatial multiplexing, that can allow us to do 2x2 MIMO, which means we can form up to two data streams, possibly doubling the throughput. For the beamforming, Wireless Insight supports three different receiver diversity techniques. The first is selection combining. This chooses the best signal. The second is equal gain combining, which combines the two data stream or the two signals that are received at the antennas by matching up their phases and combining in an optimal way. And the third is maximum ratio combining, which adjusts both the magnitudes and the phases to increase the signal to noise ratio. MRC tends to give the best answer, the strongest improvement to the signal to noise ratio, and for this demonstration we used MRC. But it would also be possible to analyze any or all of these techniques in additional simulations. So next we have the signal noise ratio calculations. Signal to interference plus noise ratio is a key measure for determining throughput of a channel. And this is simply the strength of the signal divided by the interference plus the noise. Sources of noise and interference include ambient RF noise, interference from other base stations, and interference from beams to other UEs or streams to other UE antennas. So in our scenario, we included the ambient RF noise. We didn't include any other base stations, so there's no interference. And we assumed that the interference would be fairly negligible because in this case, for fixed wireless access, any nearby base stations are also going to be beamforming, and with a minimal amount of coordination and with our stationary CPEs at the individual houses, it should be possible to focus beams at the houses that do not interfere with neighboring base stations who are serving different houses. For our ambient noise, we use some values from the literature of negative 168 dBm per hertz. So for our 100 megahertz bandwidth, this results in a negative 88 dBm noise power. And then we assumed a noise figure of 5 dB in our receivers, which further increases the ultimate received noise. Next, we estimated the peak downlink throughput for 5G NR. So Wireless Insight allows tables to be constructed that define throughput as a function of signal to noise or signal to interference plus noise ratio. For this study, we created a table of estimated throughput versus SNR based on data that was available in the literature for LTE Advanced Pro. So this allowed us to get rough estimates of throughput in megabits per second for a 20 megahertz bandwidth, which we could then scale up to the 100 megahertz bandwidth that we expect for 5G. Modulation coding schemes using this approach extend from QPSK up to 256 QAM. What these throughput estimates represent are the peak throughput for downlink transmission for for our 100 megahertz component carrier. If we were to include uplink and downlink percentages, our throughput would go down accordingly. On the other hand, if we assume that there are multiple bands and we're doing carrier aggregation, which of course we could simulate those additional bands, then we would see our throughput increase by the number of carriers. So in an actual scenario for fixed wireless access, we expect that people may have multiple carriers and that there may be some uplink downlink percentages that should be applied. For this demonstration today, however, we are going to be calculating the maximum peak throughput for our 100 megahertz component carrier. And that peak, under ideal conditions, can get up as high as 489 megabits per second. So as an initial set of simulation results, we placed a dipole where the transmitter is and ran a quick simulation to look at fields to see how the fields propagate. This also creates a baseline scenario. We start with a dipole and then we can see how much improvement we get when we start using beamforming with the MIMO antenna. So on the screen we show the field map results overlaid on a view of the scene. And this is actually, we're actually looking at Wireless Insight right now, looking at some of these results. And we can see some clear things happening here. There are some very strong fields that move forward. This is signal to interference plus noise. So we see some very strong levels of 40 to 50 dB in the direct line of sight, but we see some very sharp shadowing just behind a few trees and behind the houses as well. So as expected with millimeter waves, we have very strong line of sight and we have deep shadowing. And these are the effects that are going to be coming into play when we start trying to see how well our system performs in this neighborhood. This winding road is not going to be helpful when it comes to shadowing. So next, we looked at a simulation for the CPEs that we had placed. Now we placed CPEs at all the windows on the first floors of all the houses, and that results in a lot of data. So we have a plot on the right that shows our results. This is for our baseline dipole simulation before we bring in our beamforming. The faded lines represent all of the individual CPE locations that we have placed. So each window had 4 on the interior. Those are shown in the red, the faded red. And they had 4 on the exterior, and those are green. So what we did is we then looked at the initial sets of results and we determined which of the windows seemed to be providing the best line of sight or the best received power from the base station. And then we moved forward by creating a reduced set of receivers, the same cluster of 4 receivers, but just at those optimal windows. And we can see those in the dark red and the dark green lines. So the red is the indoor window result. Green is the outdoor window mounted CPE, and the blue are the rooftop CPEs. These are all the results for the left side of the street. There's another similar set of results for the right side of the street. So what we could see here is that the rooftops perform pretty well. We didn't have to take the best of those. They were just in a fairly optimal position on the roof. It's easy for the signal to propagate to those positions. So the dark blue line does pretty well and gets a fairly high signal to noise even without any of the beamforming. We're achieving as high as high teens or 20 dB signal to noise ratio. The exterior window mount does fairly well as well. But if we look at the red values, we can see that the interior windows drop off very quickly. And once we get beyond what's really the first few houses that are in line of sight and start to turn the corner, we start to lose power very rapidly. And the signal to noise beyond about 70-80 meters has dropped so far that it's not usable, at least in this initial configuration. So these clusters of the best of for each of the houses, to keep the plots easy to look at for the remainder of our simulations that we're going to use in this talk, we will use these clusters of receivers. If we want to get a closer look at where these optimal window positions are, we can bring up the GUI again, and we can highlight this reduced set of receivers, which colors each of the receivers in the windows yellow, and we can look at these positions. And we'll notice that in the first few windows, the first few houses, The optimal receiver positions are fairly intuitive. They're pretty close to line of sight of our base station. In one case we have a set that's behind some trees, but otherwise it's in a fairly good strong line of sight path. And right on the corner here it's difficult to see. But the optimal position again is not too far off of the line of sight. Now for the last two houses, it turns out that the optimal positions are on rear windows of the houses on the corners in the backyards, and it turns out that those positions, because of the curvature of the street, are easier to get to and closer to line of sight. The waves do have to travel through some trees, but they can reach them without any other obstructions. So following the baseline, the next thing we did is we wanted to see how much improvement we get from the MIMO beamforming. So we used the predefined beams that we discussed earlier in the pre-coding table, and we generated a new series of results for those best of windows that we talked about, and we can see those results in the dark red, green, and blue lines. Red is again the interior window positions, and the faded red was the previous set of results that we were looking at for the dipole transmitter. Green is a comparison to the dipole in the light faded green, and the blue to the blue below. So we can see here that the beamforming has given us about a 25 to 30 dB improvement over the results that we had for the SISO, or single input, single output case, which is very substantial. This is from a combination of beamforming at the transmitter, the maximum ratio combining at the receiver, and also the fact that the antenna elements are essentially patch antennas that each have some gain as well. So that combined gives us this overall improvement. Despite the improvement, we still see a very rapid drop-off in the interior window antennas, dropping below, just a little above 100 meters out, they drop below 0 dB signal-to-noise ratio. But the other two configurations seem to do fairly well all the way out to the end of the street. Now we also performed simulations using maximum ratio transmission. This is our adaptive beamforming technique. We don't present the results in the webinar because they were nearly identical to the results that we got from the beamforming table. Next, we estimated the peak downlink throughput for our 100 megahertz component carrier band. This is using our pre-coding table again with the 78 beams. So in this case, we again see that corresponding to that rapid drop in signal-noise ratio, we see a very similar drop, of course, in the throughput. So out beyond about 100 meters, the interior systems are not able to get very much throughput at all. However, for the other two configurations, the throughput is very close to, it's able to achieve some level of 256 QAM, very close to the maximum, all the way out until we get to the last house on the street, where some shadowing by trees starts to get in the way. So the two exterior mounts seem to be doing fairly well here. And the interior, of course, has a very short range. Now, one thing to keep in mind, as we talked about before, is that the results that we're showing here are for the optimal window. So this is not for any window under any conditions. It happens that there are windows that are near or close to line of sight, and we have to assume here that whoever is mounting these has found these optimal windows if they're going to achieve this type of throughput. If we were to just place the system in any random window, we already saw in the results before that some of those windows have very low signal levels, and so the throughput could drop very rapidly down to no signal at all. Next, we evaluated the spatial multiplexing. So we used the singular value decomposition and the two streams, the two beams at the CPEs in order to create two streams of data, essentially 2x2 MIMO. So we have our throughput from before, the blue, green, and red, and then the spatial multiplexing we see in the magenta and the lighter blue and lighter green. And we can see at the very close ranges, we indeed are able to get multiple streams, and we've gotten our throughput up not quite to double, but pretty close. So we were able to get streams with enough signal-to-noise ratio close in that we were able to get the throughputs up as high as 700-800 megabits per second within our band. As we move out to a little bit past 60 meters or so, these start to drop, especially for the indoor case. And as we get toward the end of the street, the spatial multiplexing is just not getting as much gain as the beamforming, and the beamforming starts to outperform. This concludes our demonstration. Thank you for joining us today. In this presentation, we showed how Remcom's tools can be used to support the design and assessment of a complex system, such as a MIMO array for 5G fixed wireless access. To carry this out, we performed a two-step process. We first showed how to design and analyze an array in XFdtd, and we then showed how to import the antenna design into Wireless Insight and assess its performance through simulation of a Suburban fixed wireless access scenario. In any actual assessment, the simulations and analysis of the results could be expanded to include additional designs, scenarios, more component carriers, perhaps to use for carrier aggregation, interference from other base stations, and many other types of studies and analysis. It's important to remember that our goal was to demonstrate a methodology that can be used to aid in the process of designing and assessing complex systems. Our example focused on 5G fixed wireless access, but the approach can be used for many other applications, and it provides a way to do virtual assessment before taking new systems out into the field. We hope that you enjoyed our presentation. We can now take questions, and once we've completed our question and answer session, if additional thoughts, comments, or questions occur to you, please feel free to contact us at the Contact Us website provided on the screen or using the sales email shown.
And now we'll take some questions. So our first question, are there upper and lower frequency limits that can be supported by the tool? And Wireless Insight has some nominal limits. We tend to state 100 megahertz up to 100 gigahertz. In reality, there isn't a true hard fixed limit. It's just that there are assumptions that somewhere below and somewhere above those bounds, we start to exceed those assumptions. So you can go above 100 gigahertz and below 100 megahertz, but generally that's the bounds that it has been designed for. There's another question about beamforming and Wireless Insight. One of our attendees has asked, can I specify the weight, amplitude, and phase of each antenna element to steer the main beam? And so in the webinar that we just demonstrated, we showed an example of a pre-coding table. We got the antenna patterns from the XFdtd tool, but then we built a pre-coding table for Wireless Insight. In that table, you could put a single beam, or you could do what we did in this demonstration where we created 78 beams. And then Wireless Insight will choose the best beam for each different receiver from that table. So the short answer is yes, you can create a single beam in that same way, and it does include both magnitude and phase adjustments for each element in the antenna. Next, have you considered using throughput estimates from the 3GPP 5G NR technical specifications, and if so, how would these affect your results? So yes, we are aware of 3GPP technical specification 38.306 from version 15.2. This includes an estimate for throughput for 5G, and it was released in June. And we have actually recently done a study very similar to this one where we used those throughput estimates instead of the ones that we used here. We found that that gave us a very similar data rate for each different signal-to-noise ratio, about maybe 10% higher actually when we use those estimates. So we believe that the results that we've shown in this webinar are reasonable. And of course, as we mentioned during the presentation, the actual throughput in a real system would be a little bit lower because of the typical at this frequency, you'd have time division duplexing, so there would be some time allocated for uplink as well.
Tarun Chavla here. There was a question on how can I define my own antenna pattern. Wireless Insight has the ability to specify antennas, analytical antennas that's built into the tool. But the format of the file is a simple text format that's documented, well documented. And we have built in converters for MSI Planet, Odyssey, and along with other 3D EM tools like CST and HFSS. Along with that, if you have specific measurement-based antenna patterns and chambers or 2D cuts from suppliers of antennas, we can build custom converters as well. There's a follow-on question about how is the scene built in Wireless Insight, the Suburban area. This was actually built using importing of shapefiles.
So the question regarding itself is, can vectors be read in a shape format? The answer is yes. We have a shapefile and a collada importer. So if you can design models outside using 3D or 2D stereo imagery, we can import any object, like a vehicle or a city with the terrain and foliage information. Follow-on questions, a couple more. Greg will take on from here.
Yes, there's a question about whether Wireless Insight, whether it has built-in MIMO capabilities, and as an example, whether it can choose the best beam for the CPE, and if not, when will those be available? So the example that we gave, this question I think popped up before we got to that point in the presentation, but it is possible to pick the best beam for each CPE, and that's how the pre-coding table actually worked. We set up, in this case, 78 beams that swept over the sector, and that's actually how the simulations worked. When they got to the communications processing, they sampled through the beams, they found the best one to each position, each CPE position within the scene, and then they used that to calculate the signal to noise and then the throughput values for that CPE. There's a question about whether we have comparisons between our simulated results and reality measured values. And yes, we do. We've done validation many times over the years. We have some validation against measured data sets from the literature in several different conditions. One of them does include millimeter wave in an indoor office area, and there's several other indoor and outdoor examples that we have as well. So for more information on that, if you could contact us, we earlier left our sales email, and we can give you more information on that. There's a question about Wireless Insight can calculate the capacity of a MIMO system. And I think this one also popped in before we showed some of our throughput results, but it is also possible to calculate the Shannon's capacity in the same manner as we calculate throughput, but then Shannon capacity is a little bit of a more generic metric, of course. There's a question about whether we support reflections from the ground. So as we showed in the presentation, there's a lot of interactions with the buildings. The simulations also did include ground reflections. They can include smooth or rough terrain. And of course, they also include attenuation from trees and interactions, both reflections and diffractions, and transmissions through materials such as walls and windows. So another example, another question in the demo, there's a question about whether the patterns that we got from the XFdtd software, whether those were individual patterns for the array elements or the beams that were shown in the XFdtd portion of the demo. It's actually the individual element patterns that get brought into Wireless Insight, and that then allows Wireless Insight to apply the MIMO techniques that we talked about, pre-coding tables or maximum ratio transmission or other types of MIMO techniques to the results, to its calculations. There's a question about whether you can model the interiors of homes and buildings, including walls and floors, and another question related to office furniture or home furniture. And the answer is yes, you can. You can model an interior floor plan. You can put multiple floors in for multi-story buildings. And in an office environment, you could put furniture as well, although usually that would be for indoor simulation. So the throughput estimates, there's a question about the fact that we did estimates for a single component carrier and a question of how this could be extended for multiple component carriers. And so we did estimates based on a single 100 megahertz component carrier. And then this, of course, could be extrapolated. If you had multiple component carriers, you could simply, you could make the assumption that you could add up the throughput from the multiple carriers. Of course, if you wanted to simulate each one in detail, you could model each component carrier at its given frequency bands. And then from those results, which would vary by frequency band, you could then sum them together to get the final answers. Okay, that's all the time that we have today. We want to thank you all for attending. Thanks again, and enjoy the rest of your day.